Our closest galactic neighbor hides a violent secret history. This is not just about the beautiful spiral disk of the Andromeda galaxy we see in pictures. Surrounding it is a vast, ghostly sphere called the galactic halo, a sparse realm of ancient stars, mysterious gas, and invisible dark matter. Within this shadowy frontier, astronomers have uncovered a menagerie of bizarre objects that defy simple explanation. By the end of this exploration, you will understand how these cosmic oddities are rewriting the story of how galaxies like our own are built. We will journey through 25 of the strangest finds, from rogue black holes and cannibalized galaxy cores to stars that simply should not exist out there. What does a galaxy's faint halo reveal about its turbulent past? The first and perhaps most profound clue was a faint river of light in the sky. For decades, astronomers mapping Andromeda noticed something odd. A vast, arching ribbon of stars stretching across the halo, so immense it defied belief. This is the giant stellar stream, a cosmic scar over 1 million light-years long. It is not a collection of random stars, but the unraveled spine of a devoured galaxy. Picture a small dwarf galaxy, once independent, swinging too close to the colossal Andromeda. The immense tidal forces, the difference in gravity between the near and far sides of the small galaxy, slowly pulled it apart like cosmic taffy. Over billions of years, its stars were stripped away and smeared into this graceful, mournful arc that now encircles the predator. Detecting this stream was a triumph of patience and precision. You cannot see it in a single photograph. It is too faint and blended with the background. Instead, astronomers painstakingly counted and mapped millions of individual stars, noting their subtle motions and chemical signatures. The stars in the stream move together, a family sharing a tragic history, and they possess a distinct chemical fingerprint different from Andromeda's native halo stars. They are older and poorer in heavy elements, a telltale sign of a small, ancient galaxy that lived and died long ago. This stream is more than a relic, it is a fossil record written in starlight. By tracing its curve and modeling its stars, scientists can rewind the cosmic clock. They can deduce when the merger happened, from what direction the victim came, and even estimate its original mass. Each stellar stream in Andromeda's halo, and there are many, is a chapter in a violent autobiography, a ledger of conquests that built the giant we see today. The quiet halo, it turns out, is a galactic graveyard, and these shimmering streams are the ghostly monuments left behind. But the cannibalized galaxy that formed the giant stream was not the only victim. When astronomers looked at the other small galaxies still orbiting Andromeda, they found a pattern so strange it seemed to defy the laws of cosmic chaos. Most of Andromeda's known dwarf satellite galaxies are not scattered randomly around it like bees around a hive. Instead, they are aligned in a vast, thin, rotating disk, a structure astronomers call the Andromeda satellite plane. Picture a colossal, invisible vinyl record with Andromeda at the center and over half of its satellite galaxies like Andromeda 2, Andromeda 3, and Andromeda 16, all spinning along the same narrow groove. This is deeply puzzling. Our standard model of cosmology, which has been incredibly successful at explaining the large-scale universe, predicts that dark matter halos should host satellites moving in all directions, a more or less spherical swarm. Finding such a precise, flattened plane of galaxies feels like throwing a handful of marbles into the air and watching them neatly arrange themselves into a spinning ring. It simply should not happen by random chance. So what is forcing these galaxies into this cosmic conga line? One compelling theory is that this plane is a fossil, a relic from the very formation of Andromeda itself. Billions of years ago, vast rivers of gas and dark matter may have flowed into the young galaxy along specific cosmic filaments. Smaller galaxies that formed within these streams would have inherited that preferred direction, locking them into the same orbital plane we see today. It is a structure frozen in time. The competing idea is far more dynamic. perhaps this plane is not ancient at all, but the result of a recent colossal collision. A single massive interaction with another galaxy could have triggered shockwaves through the halo, herding many of the dwarf galaxies into this peculiar alignment. This debate is far from settled. Every new observation of these faint dwarfs, every precise measurement of their speeds and paths adds another piece to the puzzle. The existence of this plane is a quiet but persistent challenge to our understanding, a reminder that even our best models of the universe must sometimes bend to the evidence written in the sky. One of the most glaring anomalies in that halo is not faint at all. It is a brilliant, compact pinprick of light known as Messier 32. While most of Andromeda's satellite galaxies are faint and diffuse, M32 is astonishingly bright and dense. It looks less like a full galaxy and more like the brilliant, stripped-down core of one, which is precisely what many astronomers believe it to be. This compact elliptical galaxy is an astronomical paradox. It packs a staggering number of stars into a volume only a few thousand light-years across. If you could place it at the center of our own Milky Way, its intense glow would outshine our entire galactic bulge. The strangeness does not stop with its appearance. Deep within its heart lies a supermassive black hole, a monster with a mass millions of times that of our Sun. This is expected for a large galaxy, but M32 is tiny. Its central black hole is wildly disproportionate, far more massive than it should be for such a small stellar system. It is like finding a jet engine inside a compact car. Then there are the stars themselves. While the halo is supposed to be a retirement home for ancient stars, M32 contains a surprising population of middle-aged stars, stars that are much younger than the ancient halo around it. This suggests a burst of new star formation happened relatively recently in its history, a cosmic event that should have been impossible for such a small, isolated object. The leading theory ties all these bizarre clues together into a single, violent story. Astronomers suspect M32 is the surviving heart of a much larger galaxy that ventured too close to Andromeda. In a process called tidal stripping, Andromeda's immense gravity would have violently shredded away the outer layers of that galaxy, its spiral arms and diffuse halo of stars, feeding them into the giant stream we discussed earlier. What remained was the galaxy's dense, resilient core, its central black hole, and a swirl of gas shocked into forming new stars during the chaotic merger. This remnant, this galactic nugget, is what we now call M32. It is not a born dwarf galaxy, it is a cosmic survivor, a ghost of a galaxy that was. Its very existence is a direct snapshot of galactic cannibalism in action, a dense trophy from a past meal still held within Andromeda's gravitational grip. While M32 is a dense survivor, its neighbor tells a different kind of tale. Just beyond the spiral's glow lies NGC 205, also known as Messier 110, a satellite galaxy that looks deceptively simple at first glance. Classified as a dwarf elliptical, it should be a quiet, featureless sphere of ancient red stars, a place where star formation ended eons ago. Yet this galaxy holds onto secrets. Through powerful telescopes, astronomers spotted the impossible, dark, ragged patches silhouetted against its faint light. These are lanes of interstellar dust, the raw material for building new stars. In a galaxy this small and old, such dust should have been used up billions of years ago or blown away by the explosions of ancient supernova. Its presence is a glaring anomaly, a sign that something is stirring in this supposedly dormant system. Furthermore, nestled within that dust, surveys have detected the faint blue glow of young star clusters. These are not the ancient stars expected in a dwarf elliptical, but stellar newborns, perhaps only a few 100 million years old, a blink in cosmic time. This recent spark of activity defies every expectation. How does a small, aging galaxy suddenly start making new stars? One compelling clue points directly to Andromeda itself. NGC 205 orbits through the galaxy's immense halo, which is not entirely empty. It contains vast, diffuse reservoirs of hydrogen gas. As the dwarf galaxy plows through this thin medium, the interaction could be compressing its own scant gas or even capturing new material from the halo itself. This influx of fuel, however slight, might be just enough to trigger a small, late burst of star formation, painting its old stellar population with these unexpected blue brushstrokes. Another possibility is that, like M32, this dwarf has a more violent past. The dust and young stars could be the aftermath of a merger or a close encounter that stirred up its interior, recycling old material into a new generation. Visually, NGC 205 appears as a soft, elongated smudge of light adjacent to Andromeda's bright core, but those subtle dark lanes, once discovered, transformed its story. They are a reminder that even in the quiet outskirts of a giant, evolution never truly stops. This dusty dwarf is not a static fossil. It is a system still responding to its environment, a testament to the dynamic and interconnected nature of everything within a galaxy's vast, influential reach. The ancient, dense balls of stars we call globular clusters are usually galactic homebodies. These spherical swarms, each containing hundreds of thousands of stars bound tightly together by gravity, are most often found orbiting close to a galaxy's bright central bulge. Andromeda, however, has a collection of rebels scattered throughout its immense halo far beyond the main disk. Astronomers have identified globular clusters that seem to be in entirely the wrong place. Their remote locations are the first clue to a startling truth. These are not native to Andromeda. They are cosmic orphans kidnapped during the galaxy's long history of collisions. When a small dwarf galaxy is torn apart and absorbed, its globular clusters do not simply dissolve. They are remarkably tough, held together by their own intense gravity, and they survive the ordeal. As their parent galaxy is shredded, these clusters are set adrift, eventually being captured by Andromeda's gravitational pull and joining the orbit of their new giant host. We can trace their foreign origins not just by their position, but by their very substance. Stars within a globular cluster are born from the same cloud of gas, making them chemical siblings. By analyzing the faint light from these distant clusters, astronomers can read their chemical DNA. Some clusters in Andromeda's outer halo show a distinct fingerprint. They are poorer in heavy elements like iron compared to the clusters born within Andromeda itself. This metal-poor signature is a hallmark of ancient, small galaxies that formed in the early universe before many generations of stars had cooked heavier elements. So a single, lonely globular cluster drifting in the dark halo becomes a tag, a label still attached to a galaxy that no longer exists. By cataloging the positions and chemistries of these exiled clusters, scientists are essentially conducting galactic archaeology. Each cluster is a surviving artifact from a separate act of cosmic ingestion. Mapping them allows astronomers to piece together a timeline, to understand not just that Andromeda consumed smaller galaxies, but which ones, when, and from which direction they came. These glittering, ancient star cities are more than just beautiful deep sky objects. They are forensic evidence helping to reconstruct the assembly history of an entire galaxy, one stolen gem at a time. The halo's ancient stars should glow with a cool, ruddy light, the quiet embers of the early universe. Yet scattered across that somber backdrop, astronomers find brilliant sapphire sparks. These are isolated blue stars, massive, hot, and young, burning furiously against the cosmic dark. Their very existence in the halo is a profound contradiction, like finding a sapling growing in a petrified forest. This population of stellar rebels, often called blue stragglers, presents a mystery with two equally compelling solutions. The first theory is one of stellar violence and resurrection. In the dense core of a globular cluster, ancient stars can collide or merge. Picture two old, weary suns in a tight binary dance, gradually spiraling inward over eons until they finally coalesce. This merger creates a single, more massive star, which reignites its internal nuclear furnace with fresh hydrogen fuel. The result is a star that appears younger, hotter, and bluer than its true age would allow, a stellar phoenix born from a collision. These rejuvenated stars could then be flung out into the halo by gravitational interactions, leaving them isolated far from their birthplace. The second theory is even more radical. It suggests these stars were born right where we see them. While the halo is sparse, it is not entirely empty of gas. Small, dense clouds of hydrogen, perhaps stripped from incoming dwarf galaxies or lingering from the galaxy's formation, could occasionally collapse under their own gravity. In these lonely, isolated nurseries, a new generation of stars could ignite. This in situ formation would mean the halo is not a static museum, but a place with pockets of slow, ongoing creation. Distinguishing between these origins is incredibly difficult from such vast distances. Each explanation, however, points to a dynamic and eventful halo. If the stars are merged ancients, they reveal a history of stellar encounters and gravitational scattering. If they are true newborns, they map hidden reservoirs of gas and subtle, local conditions that can still spark star formation in the most unlikely places. These solitary blue beacons are therefore critical probes. By studying their motions, their brightness, and their chemical makeup, astronomers can trace the flows of material and energy through the halo's invisible architecture. They are not just anomalies, they are clues to the ongoing, subtle processes that continue to shape the galaxy's outermost frontier, long after its main era of construction was thought to be complete. A star's velocity can tell a story of cosmic escape. Among the ancient populations of Andromeda's halo, astronomers have identified rare stars moving at breathtaking speeds, velocities so extreme they are classified as hypervelocity star candidates. These are not merely fast, they are on trajectories that could potentially break free from the galaxy's immense gravitational pull entirely, destined for the emptiness of intergalactic space. Their existence raises a thrilling question: what cosmic catapult could launch a star with such ferocious energy? The prime suspect sits at the very heart of the drama, the supermassive black hole in Andromeda's core. This invisible monster, with a mass 100 million times that of our Sun, is a gravitational powerhouse. One compelling launch mechanism involves a binary star system, two stars orbiting each other, that wanders too close to this danger. The black hole's tidal forces could violently disrupt the pair, capturing one star into a tight orbit while flinging the other away at a staggering fraction of the speed of light, like a slingshot with unimaginable power. The ejected star would carry the momentum of that entire system, becoming a hypervelocity projectile. Another possibility points to the explosive end of a stellar companion. If one star in a binary system goes supernova, the sudden, asymmetric detonation could act like a natural rocket engine, kicking the surviving star away at tremendous speed. Identifying these candidates is a feat of extreme precision. Astronomers must measure the star's motion across our line of sight and, crucially, its radial velocity, how fast it is moving toward or away from us. This requires analyzing the subtle shift in the star's light, a Doppler effect, to detect speeds that can exceed 1,000 kilometers per second. A star with such a velocity, especially one in the remote halo where everything else moves more sedately, immediately stands out. The trajectories of these escapees are cosmic breadcrumbs leading back to their origin. By tracing their paths backward through computer models, scientists can attempt to pinpoint where in the galaxy they were launched from. A cluster of such stars with paths converging near the galactic center would be strong evidence for the black hole slingshot mechanism, revealing a history of violent gravitational encounters in Andromeda's crowded core. Each hypervelocity candidate is therefore a forensic probe, a piece of evidence hurled from the scene of a past catastrophe, telling us about the most extreme environments a star can survive and the invisible forces that can send it on a one-way journey into the void. Dark matter remains the universe's most stubborn ghost, felt only by its gravitational pull. Yet in Andromeda's halo, astronomers may have found its faint fingerprints, not by seeing it, but by watching how it bends the light of other things. The key lies in those graceful rivers of stars, the stellar streams formed from devoured galaxies. In a perfectly smooth halo of dark matter, these streams should flow in elegant, undisturbed arcs. But what if the stream shows a kink, a gap, or a sudden wiggle? That distortion could be the sign of an invisible passerby, a dense clump of dark matter known as a subhalo. These are not full galaxies, but smaller, self-contained knots of dark matter that should, according to our leading cosmological model, pepper the halo in vast numbers. They are the predicted building blocks of larger structures, the cosmic scaffolding left over from the universe's youth. Spotting them directly is impossible, but their gravity leaves a mark. As one of these invisible subhalos passes through or near a stellar stream, its gravitational tug pulls on the stream's stars, disturbing their orderly flow like a stone dropped into a smooth flowing river. The resulting perturbation, a subtle warping or a break in the stellar line, is a clue that something massive but unseen just went by. Finding these disturbances in Andromeda's streams is a critical test. The Lambda CDM model, our standard blueprint for the universe, makes very specific predictions about how many dark matter subhalos of a certain size should exist around a galaxy like Andromeda. By carefully mapping the stellar streams in its halo and searching for these telltale gaps and wiggles, astronomers can count the number of gravitational disturbances and compare it to the model's predictions. A match would be a powerful confirmation of our understanding of dark matter's clumpy nature on the scale of individual galaxies. A significant mismatch, however, could signal a crisis. If there are far fewer gaps than expected, it might mean dark matter subhalos are being destroyed or smoothed out by processes we do not yet understand, or it could hint at deeper mysteries about the nature of dark matter itself. Is it colder or warmer than we think, affecting how it clumps? Each distorted stream in Andromeda's halo is therefore more than a relic of past mergers. It is a living experiment. By reading the ripples in these rivers of stars, we are not just looking at the history of light, but probing the hidden architecture of the invisible universe, testing the very rules we believe govern all of cosmic structure. The hunt for hypervelocity stars reveals the halo's violent dynamics, but other discoveries point to its quiet, ancient foundations. In the farthest, darkest reaches of Andromeda's halo, astronomers have found the most ghostly galaxies imaginable, the ultrafaint dwarfs. These are not collections of billions of stars, but mere smudges of a few thousand, sometimes just a few hundred, spread across volumes hundreds of light-years wide. Their light is so feeble that detecting them against the glow of the night sky and the backdrop of Andromeda itself is one of modern astronomy's greatest technical challenges. It requires painstaking surveys with the world's most powerful telescopes, peeling back layer after layer of sky to reveal these faintest of cosmic whispers. Examples like Andromeda 19 and Andromeda 21 are so diffuse they barely qualify as galaxies at all, more like stellar mist held together by a secret. That secret is an overwhelming amount of dark matter. These ultrafaint dwarfs are by far the most dark matter-dominated objects we know of in the universe. For every single visible star shining in one of these systems, there may be thousands of solar masses of invisible dark matter providing the gravitational glue that keeps it from simply dissipating into the void. This extreme ratio makes them pristine laboratories. Because they are so small and formed so early, they were largely untouched by the turbulent star-forming processes that enriched larger galaxies with heavy elements. Their stars are pure, ancient relics composed almost entirely of hydrogen and helium, the primordial elements forged in the Big Bang. Studying them is like looking at fossilized pieces of the universe's first structures. Their strange, spread-out structures tell a story of arrested development. Unlike the dense cores of globular clusters, these dwarfs never had enough gas or the right conditions to collapse into a tight, shining ball. They represent a failed path of galactic evolution, a first attempt at building something larger that simply stalled billions of years ago. Each one is a cosmic time capsule, preserving the conditions of the early universe in near-perfect isolation. Finding and mapping them around Andromeda is crucial because their distribution and properties test our theories about how the very first galaxies formed and how they were drawn into the halos of giants like Andromeda. Every faint, new smudge discovered on the edge of perception is not just another satellite. It is a direct window into the universe's childhood, a shadow from a time when the cosmos was a much darker, simpler, and more mysterious place. The chemical story of the halo takes a strange turn with a particular class of crimson giants. Amidst the ancient metal-poor stars, astronomers have identified a population of carbon stars, cool, luminous giants that glow with a distinct, deep red hue. Their atmospheres are not just poor in heavy elements, they are chemically inverted. Normally, in a star like our Sun, oxygen is more abundant than carbon. But in these aging giants, chemical processes have dredged up carbon from the stellar interior, flooding the atmosphere until carbon atoms outnumber oxygen. This creates a sooty, carbon-rich shroud that filters the star's light, giving it that characteristic ruby glow. Finding such stars in the halo is unexpected. They are typically associated with the disk of a galaxy, where stars are richer in metals and can evolve through this specific late life phase. Their presence in the sparse, primordial halo is a chemical puzzle. So how did these carbon-rich giants end up so far from home? One compelling origin story ties them directly to Andromeda's own violent growth. They may not be native to the halo at all, but rather ancient migrants. These stars could have formed billions of years ago within Andromeda's own early disk, when it was smaller and more chemically primitive. Later, during a major merger with another galaxy, the immense gravitational turbulence could have flung these stars out from the disk and into the distant halo where they now live out their final days. Their chemical fingerprint, while carbon-rich, still shows the low overall metal content of that early era, a tag confirming their origin in Andromeda's youth. The alternative theory paints them as cosmic immigrants in a different way. Perhaps these carbon stars were born in small, dwarf galaxies that Andromeda later consumed. In those isolated environments with their own unique chemical histories, stars could have evolved along paths that favored the production of carbon. When their host galaxy was torn apart, these crimson giants were deposited into Andromeda's halo like exotic seeds from a foreign garden. Their value to astronomers is immense. By mapping the locations and motions of these distinct red stars, scientists can trace the flow of material from past mergers. A cluster of carbon stars following a specific path could mark the orbital trail of a long-dead dwarf galaxy. They serve as brilliant chemical tracers, their sooty light acting as a highlighter pen across the halo, illuminating chapters of accretion history that would otherwise remain invisible. Each one is a dying ember that tells a story of its birth, a story of either exile from the inner galaxy or a long journey from a galaxy that no longer exists. The final breaths of sun-like stars paint the halo with ephemeral beauty. Scattered across that vast, dark volume are delicate, glowing shells of gas known as planetary nebulae. Each one is a cosmic butterfly, the brilliant, expelled atmosphere of a dying star, illuminated by the intense ultraviolet light from the tiny, hot stellar core left behind. These objects are fleeting, lasting only a few tens of thousands of years before they dissipate into the interstellar void, which makes finding them in the halo a remarkable feat. Their presence, however, is more than a visual spectacle. It is a direct contradiction to our expectations. The halo is supposed to be dominated by ancient stars that formed over 10 billion years ago. Stars massive enough to die as supernova would have done so long ago, and the lowest mass red dwarfs live for trillions of years. But Sun-like stars with lifetimes of roughly 10 billion years occupy a middle ground. To see the glowing shrouds of their death scattered throughout the halo means a significant population of these intermediate age stars must exist out there. This forces a difficult question: where did these stars, which are not ancient enough to be native to the primordial halo, come from? The answer lies in the chemical story written in the nebulae themselves. By analyzing the specific colors of their light, astronomers can determine their composition. The abundance of elements like oxygen, nitrogen, and helium forged in the star's interior and then ejected into space. This chemical fingerprint is unique, a signature inherited from the cloud of gas in which the star was born billions of years earlier. When scientists examine the planetary nebulae in Andromeda's halo, they do not find a single, uniform signature. Instead, they discover distinct families, groups of nebulae with similar chemical patterns that differ from the nebulae found in Andromeda's main disk. This is the critical evidence. These chemical families are the ghosts of separate galaxies. Each family represents a group of stars that formed together in a now devoured dwarf galaxy, sharing that galaxy's particular chemical history. When their host galaxy was assimilated, these stars, along with the gas that would later form their planetary nebulae, were scattered into the halo. Now, in their death throes, they reveal their foreign origins. A planetary nebula glowing faintly in the remote halo is therefore a dual marker. First, its very existence points to a past epoch of star formation in a galaxy that no longer exists. Second, its specific chemistry tells us about the conditions in that lost galaxy. Was it rich in certain elements? Did it have bursts of star formation? By cataloging these beautiful, fading objects, astronomers are not just mapping where stars die, they are reading the obituaries of entire galactic systems, using the final, glowing size of their stars to reconstruct histories that were erased billions of years ago. Death is not always a quiet affair in the halo. Some of its most energetic objects are invisible to our eyes, revealing themselves only through a torrent of high-energy radiation. Astronomers scanning Andromeda with space-based X-ray telescopes have pinpointed brilliant, flickering beacons scattered far from the galaxy's star-forming disk. These are X-ray binary systems, and their presence in the ancient halo is a violent paradox. An X-ray binary is a cosmic vampire, a pair of stars locked in a lethal dance. One member is a normal star, while its companion is the stellar corpse of extreme density, a neutron star or a stellar mass black hole. The immense gravity of this dead star relentlessly pulls gas from the outer layers of its living partner. This stolen material does not fall quietly. As it spirals inward at nearly the speed of light, it forms a superheated disk around the compact object, a maelstrom of plasma so hot it glows not with visible light but with fierce X-rays. These systems are lighthouses of high-energy physics, but they have a very short lifespan by cosmic standards, typically only lasting a few million years. This is the core of the mystery. The halo is a retirement home for stars over 10 billion years old, far too ancient to host such short-lived volatile systems. Finding these brilliant X-ray beacons out there is like discovering a roaring campfire in the middle of a petrified forest. So how did they get there? One dramatic possibility is that they were violently ejected from their birthplace. The supernova explosion that created the neutron star or black hole could have been lopsided, delivering a tremendous kick to the newborn corpse. This natal kick could have been powerful enough to launch the entire binary system out of the crowded galactic disk and into the remote halo, where it continues its vampiric feast far from home. Another explosive scenario involves a close encounter in a dense star cluster. A gravitational interaction with a third star could have slingshotted the binary system out into the galactic hinterlands. The second theory ties them directly to Andromeda's history of galactic feasts. These X-ray binaries might not be refugees from the disk at all, but relics of ancient mergers. They could have formed billions of years ago within a small dwarf galaxy that was later consumed. When that galaxy was torn apart, the binary system survived the ordeal and was deposited into Andromeda's halo, where it has been slowly consuming itself ever since. Their enduring activity suggests the companion star might be a long-lived red giant, providing a slow, steady stream of fuel over eons. Distinguishing between these origins requires meticulous detective work. By measuring the precise positions and intensities of these X-ray sources and overlaying them on deep optical images, astronomers look for clues. Is the binary system isolated against the dark halo, suggesting a high-velocity ejection? Or is it embedded within a faint stream of stars, tagging it as an immigrant from a devoured galaxy? Each flickering point of X-ray light is therefore a signpost pointing to a past cataclysm, either a stellar explosion powerful enough to hurl a star system across the galaxy, or a galactic collision that stranded it in the deep dark. They remind us that the halo is not a serene backwater, but a repository for the most energetic aftermaths the universe can produce. The flickering X-ray beacons reveal violent histories, but the halo also holds steadier, more rhythmic lighthouses. Among its ancient red giants, a special class of stars pulses with a slow, predictable heartbeat. These are Mera variables, named for the prototype star Mera in the constellation Cetus. They are aging suns in their final stages, swelling and shrinking in a regular cycle over periods of several hundred days, their brightness waxing and waning by a factor of 100 or more. This remarkable regularity makes them invaluable cosmic tools known as standard candles, because the intrinsic brightness of a Mera variable is directly tied to the length of its pulsation period. Astronomers can determine exactly how luminous it truly is. By then comparing that known luminosity to how faint it appears in the sky, they can calculate its distance with remarkable precision. It is like knowing the exact wattage of a light bulb and using its apparent dimness to judge how far away it is. Large-scale surveys have now identified thousands of these pulsating giants scattered throughout Andromeda's halo, transforming them from mere stars into a three-dimensional mapping grid. Each Mera variable provides a precise distance measurement to its specific location in the halo. By compiling these measurements, astronomers have been able to construct the most detailed three-dimensional map ever made of a galactic halo's structure. This map revealed something unexpected. The halo is not a perfect, round sphere of stars surrounding Andromeda. Instead, it is somewhat flattened like a squashed ball. This subtle deformation is a critical clue. A perfectly spherical halo would suggest a quiet, isolated formation where stars and dark matter settled into a smooth, symmetrical distribution. A flattened halo, however, points to a dynamic and messy construction process. The shape implies that Andromeda did not form in place from a single, collapsing cloud, but was built up over time through a series of mergers, many of which likely happened along a preferred plane, much like the disk of satellites we discussed earlier. These accretion events would have deposited stars and dark matter in a way that imparted a slight overall spin or alignment to the outer halo, leading to its flattened form. Furthermore, the degree of this flattening tells us about the dark matter itself. The shape of the visible stellar halo is sculpted by the gravitational pull of the invisible dark matter halo that surrounds it. The flattening we see suggests that the dark matter distribution is also not perfectly spherical, influencing how the visible tracers, like the Mera variables, are arranged in space. Each pulsating red giant, with its slow and steady rhythm, has become a surveyor's pin in the cosmic map, helping to trace the true, warped shape of Andromeda's vast domain, and by extension, the hidden hand of the dark matter that governs it. Some of the loneliest objects in the cosmos are not found within any galaxy at all. Drifting through the immense voids between galaxies are rogue star clusters, entire cities of stars that have been flung from their homes or formed in the deep dark, now wandering the cosmic wilderness. Andromeda's vast halo acts as a net, capturing some of these nomadic clusters as they pass through, offering us a chance to study these elusive intergalactic travelers. The very idea challenges our understanding of where stars can live. A star cluster is a massive, gravitationally bound family of stars, typically born together from a single giant cloud of gas. We expect to find them orbiting within galaxies where such dense gas clouds exist. The notion of a cluster floating freely in the almost perfect vacuum of intergalactic space seems almost impossible. Yet, the evidence suggests they are out there. How could such an object come to be? One dramatic origin story begins with violence. During a galactic merger or a close encounter, the immense tidal forces can pluck entire clusters from the outer regions of a galaxy, hurling them into the void with enough speed to escape forever. It is a form of cosmic eviction on a colossal scale. Another, even more fascinating possibility is that some of these clusters formed in situ, right there in intergalactic space. In the early universe, vast filaments of dark matter and gas stretched between emerging galaxies like a cosmic web. At the intersections of these filaments, conditions might have been just right for pockets of gas to collapse and ignite stars, forming clusters that were never part of a traditional galaxy at all. They would be true orphans born of the void itself. Identifying these intergalactic interlopers within Andromeda's halo is a profound challenge. They look, through our telescopes, almost identical to the native globular clusters that have always belonged to Andromeda or those stolen from devoured dwarf galaxies. The key to telling them apart lies in their motion and their chemistry. A captured intergalactic cluster would be moving on a very different trajectory compared to the rest of the halo population, perhaps on a highly eccentric or retrograde orbit that betrays an external origin. More tellingly, its chemical fingerprint could be truly unique. If it formed in isolation in a pristine filament of the early universe, its stars might show an elemental purity even greater than the oldest halo clusters, a signature of gas untouched by the pollution of generations of supernova from a larger galactic environment. Finding such a pristine object would be like discovering a perfectly preserved fossil from the universe's first few 100 million years. These nomadic clusters represent an extreme end of the galactic ecosystem. They are the ultimate survivors, enduring eons of darkness between the islands of light we call galaxies. Their capture by Andromeda is a fleeting moment in cosmic time, a temporary harbor for a traveler that may one day be ejected back into the void. Studying them offers a chance to probe conditions in environments we rarely get to sample, the vast and empty intergalactic medium itself. Each candidate cluster, with its strange path and ancient light, asks us to reconsider the boundaries of galactic influence and the lonely journeys that some stellar families have endured since the dawn of time. The fuel for future stars is already raining down from the void. Drifting silently through the immense darkness of Andromeda's halo are colossal, invisible rivers of gas known as high-velocity clouds. These are not collections of stars, but vast reservoirs of neutral hydrogen, the most basic building block of the universe, each cloud containing enough raw material to forge millions of suns. They are detected not by the light they emit, but by the faint radio whispers of their hydrogen atoms. Using giant radio telescopes, astronomers can tune into a specific frequency, a signature emitted when the single electron in a hydrogen atom flips its spin. By mapping this signal, they reveal the ghostly outlines of these structures, some spanning tens of thousands of light years, moving at speeds that defy simple orbits. Their very name, high-velocity cloud, comes from this motion, as they appear to be streaming through or falling into the halo at peculiar, often unexpected velocities. Their origin is a subject of intense debate, with two primary theories painting very different pictures of the cosmic environment. The first suggests these clouds are primordial, ancient relics of the cosmic web itself. After the Big Bang, the universe was not smooth. It was a vast filamentary network of dark matter and gas. These clouds could be leftover strands of that primordial hydrogen, never incorporated into a galaxy, now finally being drawn into Andromeda's gravitational embrace after billions of years of drifting in intergalactic space. They would be the purest, most uncontaminated gas in the local universe. The second theory ties them directly to the galaxy's violent history. They could be the shredded remains of dwarf galaxies that ventured too close. When a small satellite galaxy is torn apart by tidal forces, its stars are pulled into streams, but its diffuse halo of gas is even easier to strip away. This gas, stretched and fragmented, could manifest as these high-velocity clouds, the lingering breath of a galaxy that was consumed. Their significance is profound, for they represent the future potential of Andromeda. This infalling hydrogen is fresh fuel. If and when these clouds eventually sink toward the galactic disk, their compression could trigger new waves of star formation billions of years from now. They are a delivery of cosmic groceries, ensuring the galaxy does not simply run out of gas and fade away, but perhaps their greatest role is as tracers. Because they are so diffuse and responsive to gravity, their motions map the invisible architecture of the halo and the cosmic web filaments that feed it. By following their paths, astronomers can chart the flows of material on the largest scales, watching as the galaxy breathes in, slowly gathering the resources for its next act of creation from the dark rivers that flow between the stars. But the halo is not just a graveyard, it may also be a nursery. Amidst the debris of ancient collisions, astronomers have spotted something that seems to be growing. These are bright, dense knots of gas and young stars found within the immense stellar streams themselves, and they are candidates for a revolutionary idea titled dwarf galaxies. This concept turns our understanding of galaxy formation on its head. We have always thought that galaxies are born from the top down, where vast halos of dark matter form first, and their gravity then pulls in gas to create stars. A tidal dwarf galaxy would form from the bottom up, built purely from the visible, baryonic matter cast off during a galactic collision. Picture two massive galaxies merging. As they swing past each other, their gravitational forces pull out immense tidal tails of gas and stars like spiral arms stretched to their breaking point. Within these tidal tails, the densest pockets of gas can collapse under their own gravity, igniting furious bursts of star formation. If such a pocket is massive enough, it could potentially hold itself together as a distinct, gravitationally bound object. A new galaxy born not from a dark matter seed, but from the wreckage of a cosmic accident. In Andromeda's halo, astronomers have identified several of these intriguing candidates. They appear as unusually bright, blue, and compact clumps embedded within the faint rivers of stars from past mergers. They are rich in gas and are actively forming new stars, a stark contrast to the ancient, red populations that dominate the halo. The great debate centers on whether these clumps are truly independent. Are they just temporary, bright star-forming regions that will eventually be pulled apart and absorbed back into the halo? Or have they achieved enough mass and self-gravity to survive as long-lived dwarf galaxies? Determining this is incredibly difficult from our distant vantage point. The key test is to measure their mass. If they are held together primarily by their own visible stars and gas, they are true tidal dwarfs. If, however, they contain a significant amount of invisible dark matter, they are likely just the dense cores of the original dwarf galaxies that were shredded, not new formations. So far, measurements of these candidates suggest they are remarkably deficient in dark matter, pointing toward the tidal dwarf interpretation. If confirmed, the implications are profound. It would prove that galaxies can be built from the recycled material of cosmic crashes, creating a second generation of stellar systems without the need for a pre-existing dark matter halo. This challenges the strict hierarchy of structure formation, suggesting the universe can create galaxies through at least two completely different pathways, top-down from dark matter and bottom-up from collisional debris. These objects, glowing with newborn stars in the shadow of destruction, represent a potential new chapter in galactic evolution, one where creation rises directly from the ashes of catastrophe. The final breaths of dying suns hold the chemical history of the entire halo. When we look at the faint, collective glow of Andromeda's outer reaches, most of that light comes from a vast population of red giant stars. These are the swollen, late-life phases of ancient suns burning with a steady, ruddy glow. To the untrained eye, they might all look the same, but to a spectrograph, each one tells a unique story of its birth. By breaking their light into a rainbow, astronomers can read the specific signatures or absorption lines of different elements in a star's outer atmosphere. This reveals its metallicity, the amount of elements heavier than hydrogen and helium it contains. In the halo, this reading produces a startling result, a chaotic symphony of metallicities, not a single, uniform tune. Some stars are incredibly metal-poor, with heavy element levels hundreds of times lower than our Sun, true fossils from the universe's first billion years. Others show a surprising amount of metals, indicating they formed from gas already enriched by generations of earlier supernova. This wide range is the first clue that the halo stars did not all form in the same place or time. They are a mixed population, a cosmic melting pot of different origins, but when astronomers plot these stars on a map, a clear and powerful pattern emerges, a metallicity gradient. Stars closer to Andromeda's bright center tend, on average, to have higher metallicities. As you move farther out into the remote halo, the average metallicity of the red giants drops significantly. The most distant stars are almost purely hydrogen and helium. This gradient is not random, it is a direct fossil record of how Andromeda built itself. Think of it like the rings of a tree or layers of sediment in a canyon wall. The innermost regions of the galaxy, including its bulge and inner halo, formed first from the collapse of a primordial cloud. That early collapse triggered rapid star formation and supernova, which quickly polluted the surrounding gas with heavy elements. The next generations of stars born in that inner region, therefore, started with a higher metallicity. As the galaxy grew, it began to cannibalize smaller neighbors. These incoming dwarf galaxies, which themselves formed in isolation and are typically metal-poor, were torn apart. Their stars were scattered, but they were preferentially deposited in the outer halo because that's where the tidal forces during a merger have the greatest reach. Meanwhile, later mergers with somewhat larger, more evolved galaxies brought in more metal-rich stars, which tended to settle closer to the center due to dynamical friction, a kind of gravitational drag. The result is a clear archaeological stratification. The metal-rich stars near the center tell of Andromeda's early, intense growth and enrichment. The metal-poor stars in the far halo are the captured fossils of the first pristine galaxies to be consumed. This metallicity gradient is therefore a silent testimony to a fundamental rule. Andromeda assembled itself from the inside out, with each captured galaxy adding a new layer to its history, its chemistry forever marking its place in the galactic hierarchy. That chemical stratification is not the only map we can make of the halo's violent past. The most direct visual evidence comes from a monumental scientific effort, the Pan-Andromeda Archaeological Survey, known as P&AS. This project used the Canada-France-Hawaii telescope to painstakingly image a staggering area of sky around Andromeda, an area equivalent to over 100 full moons in exquisite detail. Its goal was to map the faintest light in the halo, and the resulting picture is nothing short of revolutionary. It revealed that the halo is not a smooth, featureless cloud of ancient stars. Instead, it is a chaotic, tangled web of overlapping stellar streams, vast shell-like structures, and faint, diffuse clumps. This map is the smoking gun for hierarchical galaxy formation, the theory that giant galaxies are built from the cannibalization of smaller ones. Every swirl and arc you see in that image is a fossilized imprint of a past merger, a cosmic crime scene frozen in starlight. The complexity is breathtaking. It shows that the giant stellar stream is just one of many, with other, fainter rivers crisscrossing the halo. It reveals giant, concentric shells of stars, like ripples from a stone dropped in a pond, which form when a small galaxy plunges directly through the center of a larger one, creating oscillating waves of stars. And it shows the splattered remains of countless smaller dwarfs, their stars not yet fully mixed into the smooth background. This map is not just a picture, it is a timeline. Astronomers use sophisticated computer simulations to play a cosmic matching game. They create virtual models of dwarf galaxies of different sizes and orbits, and then simulate their destruction within Andromeda's gravitational field. They then compare the simulated debris, the streams and shells, to the actual structures seen in the P and as map. When a simulation produces a pattern that matches a real structure in the halo, they have likely reconstructed that specific merger event. They can determine the mass of the devoured galaxy, its orbital path, and even estimate when the collision occurred billions of years ago. It is like reconstructing the sequence of a multi-car pileup by studying the final pattern of debris on the highway. By doing this for dozens of structures, scientists are piecing together Andromeda's cosmic family tree. They can identify which streams belong to the same ancestral galaxy, which shells were caused by a particularly dramatic head-on collision, and how these events contributed stars to different parts of the halo. This map transforms the halo from a simple backdrop into a dynamic, three-dimensional history book. Each faint stream is a chapter, each shell a paragraph, telling the story of how a giant galaxy slowly assembled itself from the pieces of its neighbors, a story written not in ink, but in the borrowed light of 100 billion ancient suns. Deep within that map of stellar debris, another kind of hunter may be hiding. Among the ancient globular clusters or faint dwarf galaxies drifting in the halo, astronomers are tracking a ghost with a specific, unsettling mass. This is the hunt for an intermediate mass black hole, a cosmic missing link that has stubbornly evaded definitive discovery. While we have found plenty of stellar mass black holes, the remnants of collapsed giant stars, and we know supermassive monsters lurk in galactic cores, the space between these extremes is a profound mystery. An intermediate mass black hole would weigh in at anywhere from 100 to 100,000 times the mass of our Sun. It would be too heavy to form from a single dying star, yet not nearly massive enough to anchor a galaxy's center. So how could such an object even exist? One compelling birthplace is within the dense core of a massive globular cluster. Over billions of years, repeated stellar collisions and mergers in that crowded environment could build up an object of this staggering heft, a dark nucleus grown from the cannibalized remains of many stars. Alternatively, it could be the stripped-down remnant of a dwarf galaxy's core, much like M32, but with its supermassive black hole pared down to this intermediate range by tidal forces. The evidence for one in Andromeda's halo is tantalizing but indirect. It might reveal itself through the frenzied motion of stars at the heart of a globular cluster, stars whirling around an invisible, massive pivot point at impossible speeds. Or it could flare to life as an ultraluminous X-ray source, a beacon shining from a dwarf galaxy, where gas torn from a companion star heats to incredible temperatures as it spirals into the black hole's grip. These flares are millions of times brighter than typical stellar mass black hole binaries, suggesting a more powerful, more massive gravitational engine at work. Finding a confirmed intermediate mass black hole would be a watershed moment in astronomy. These objects are the leading candidates for the seeds that grew into the supermassive black holes we see today. In the early universe, these intermediate seeds could have formed from the collapse of primordial gas clouds or the first massive stars. They would then sink to the centers of merging proto-galaxies, merging with each other and accreting vast amounts of gas to become the billion solar mass giants that now power quasars and rule galactic cores. Without finding these seeds, our story of how supermassive black holes came to be has a glaring gap. The ongoing hunt in Andromeda's halo is a meticulous process of elimination. Every unusual X-ray flare or knot of fast-moving stars is scrutinized. Could the motion be explained by a dense cluster of neutron stars? Could the X-ray flare be from a less exotic object? Each candidate must survive this rigorous gauntlet of tests. A confirmed detection would do more than just fill a catalog. It would validate a crucial chapter in the life story of every large galaxy, proving that the titans at their hearts grew from humbler, darker beginnings, some of which still wander the outskirts, silent remnants of the universe's first acts of creation. These galactic expatriates are known as extended disk stars, and their presence is a quiet rebellion against cosmic geography. They are chemically identical to the stars in Andromeda's bustling, star-forming thin disk, rich with the metals forged in generations of supernova, and they move with the same orderly, circular motion. Yet they are found thousands of light-years above and below that flat plane, deep within the sparse halo where they simply do not belong. It is as if you found a modern city dweller, dressed in contemporary clothes and speaking a familiar language, living alone in the middle of an ancient, untouched forest. Their existence forces a question: how did these sophisticated urbanites end up in the primordial wilderness? The answer lies in the gravitational tremors of Andromeda's violent past. One pathway is through a dramatic ejection. A star peacefully orbiting in the disk can have its life upended by a close encounter with a dense object, like a giant molecular cloud or another star cluster. This gravitational slingshot can kick the star out of the disk entirely, sending it on a high-velocity journey into the halo. While it retains the chemical signature of its birthplace, its new, plunging orbit marks it as an exile. The second, and perhaps more significant, mechanism is a process called dynamical heating. Picture the smooth, flat disk of a young galaxy as a calm sheet of water. Now imagine throwing a large stone into its center. The impact sends ripples and waves across the entire surface, disturbing its perfect flatness. In galactic terms, that stone is a merging dwarf galaxy. When a substantial satellite galaxy plunges through Andromeda's disk, its gravitational disturbance acts like a tremor, imparting energy to the disk stars. This energy puffs up the disk, scattering a population of stars into thicker, more extended orbits that reach far into the halo. With each major merger, the disk gets a little hotter, a little thicker, and more of its stars are scattered into this extended corona. These stars are therefore more than just misplaced objects. They are a living record of the shocks Andromeda has endured. By studying their distribution and motions, astronomers can gauge the intensity of past mergers. A large population of extended disk stars suggests a history of significant dynamical heating, pointing to mergers with fairly massive galaxies. Their very presence blurs the traditional, clean boundary between the ordered disk and the chaotic halo, revealing that these components are not isolated but continuously interacting. The halo is not just a collection of captured outsiders, it is also seeded with refugees from the galaxy's own heart, stars displaced by the very violence that built their home. The halo's ancient stillness was once shattered by a sudden, violent dawn. In the year 2010, a brilliant new light appeared in Andromeda's outer reaches, a beacon so intense it was visible in amateur telescopes. This was not a supernova, but something even rarer, a titanic eruption from a luminous blue variable star, a monstrous, unstable behemoth in a class of its own. For a brief period, this single star flared with the power of millions of suns, casting its fierce blue light across the dark halo before fading back into obscurity. Catching such an event is a once-in-a-lifetime astronomical opportunity, and finding it so far from the galaxy's star-forming heart makes it a profound mystery. Luminous blue variables are among the most massive and volatile stars in existence, often hundreds of times the mass of our Sun and millions of times brighter. They exist on the precipice, prone to colossal outbursts where they shed entire solar masses of material in violent, episodic eruptions before their ultimate fate as a supernova or even a direct collapse into a black hole. They are the rarest of cosmic celebrities, and they are not supposed to perform in empty theaters. Their natural habitat is within the dense, gas-rich clusters of a galaxy's spiral arms where such stellar giants are born. So what was one doing, erupting alone in the galactic hinterlands? The star's remote location points to two dramatic origin stories. The first casts it as a runaway, a stellar fugitive. Born in a crowded cluster within Andromeda's disk, it could have received a tremendous gravitational kick from a close encounter with other massive stars or even a black hole. This kick would have ejected it at high speed, sending it on a one-way journey into the halo where, thousands of years later, it underwent its spectacular eruption far from its birthplace. The second story is even more radical. It suggests the star formed right where we saw it flare. This would imply the existence of a very small, very isolated pocket of dense gas in the halo, a remote nursery capable of forging a stellar titan all on its own. Such an event would force us to completely rethink the conditions necessary for creating the universe's most massive stars. The significance of witnessing this outburst extends far beyond the spectacle. For astronomers, it was a fleeting chance to study the violent mechanics of mass loss in extreme detail. The light from the eruption carried fingerprints of the elements being hurled into space, offering a real-time lab for understanding how these stars enrich the cosmos with heavy elements. Furthermore, its very presence in the halo acts as a probe. If it is a runaway, tracing its path backward could lead us to its birthplace, revealing the dynamics of the dense cluster that expelled it. If it formed in situ, it maps a hidden reservoir of star-forming potential in the most unlikely of places. That single, brilliant point of blue light, now faded, leaves behind a critical question about the halo's capacity for both harboring and creating stellar extremophiles, reminding us that even the oldest, quietest places can still produce sudden, brilliant acts of violence. These chemical time capsules reveal a universe in a violent hurry. Within Andromeda's halo, astronomers have pinpointed a special class of ancient stars that carry a contradictory signature. They are extremely poor in iron, but surprisingly rich in a specific family of elements known as alpha elements. This includes oxygen, magnesium, silicon, and calcium. This specific chemical fingerprint is not a random anomaly. It is a direct record of the timeline of star formation in the universe's first galaxies. To understand why, we need to look at how elements are forged. Different elements are created by different cosmic events and on different schedules. Iron is primarily produced in the final, catastrophic explosions of the most massive stars, known as Type II supernova, but it is also produced in enormous quantities by a very specific kind of stellar death, the thermonuclear explosion of a white dwarf star called a Type I, a supernova. These Type I explosions are delayed. They occur billions of years after a star is born, once a white dwarf in a binary system slowly accretes enough mass to trigger a runaway fusion reaction. Alpha elements, on the other hand, are almost exclusively the product of those core collapse, Type II supernova from short-lived massive stars. So, the chemical story written in these halo stars tells us this. They formed from gas that was enriched by many generations of massive stars that lived fast and died young in Type II explosions. But before any significant number of the delayed Type I, a supernova had time to occur and flood the environment with iron. This means the dwarf galaxy that gave birth to these stars experienced a ferociously intense but brief burst of star formation. It was a cosmic boomtown where giant stars were born and exploded in rapid succession, seeding the gas with alpha elements, but then the star formation shut down or the galaxy was disrupted before the slower, iron-producing white dwarf explosions could contribute their material. The stars that then formed from this gas captured this unique moment, becoming metal-poor but alpha-rich. Finding these stars in Andromeda's halo is like discovering a perfectly preserved archaeological layer. They are not the absolute first stars, which would have no heavy elements at all, but they are the second generation, the immediate offspring of the universe's first major wave of star death. Their chemistry acts as a cosmic clock, allowing astronomers to date the star formation history of the long-vanished dwarf galaxies they came from. By measuring the exact ratios of alpha elements to iron in these stars, scientists can calibrate sophisticated models of galactic chemical evolution. They can determine how long that initial burst of star formation lasted, how massive the progenitor galaxy was, and even estimate when it was ultimately consumed by Andromeda. Each of these faint points of light is therefore a precise data point, a calibration tool that helps us understand the tempo of the early universe, a time when the first small galaxies flared to life in brilliant, violent bursts, painting the cosmos with the first complex elements before falling silent, their legacy carried within stars now scattered in the halo of a giant. The halo holds a light we can barely see, a faint, pervasive glow that has nothing to do with stars. This is diffuse ionized gas, a thin, hot plasma of hydrogen atoms that have lost their electrons, spread across thousands of light years. It is the most tenuous component of the galactic atmosphere, and its very existence out there is a quiet but persistent puzzle. To create this glow, you need a powerful source of energy, something capable of stripping electrons from hydrogen atoms, a process called ionization. Near the bustling disk of a galaxy, this is easy to explain. Massive, hot, blue stars flood their surroundings with intense ultraviolet radiation, ionizing the gas in great bubbles around them. But the halo is supposed to be a dark, quiet place, far from such stellar power plants. So what is ionizing the gas on this galactic scale? One possibility is that we are seeing a cosmic light leak. Perhaps the combined ultraviolet output from all the hot stars in Andromeda's disk is so immense that some of it escapes vertically, punching out into the halo and illuminating the sparse gas from below, like a city's light pollution glowing in a distant fog. While plausible, models suggest this starlight alone may not be powerful enough to explain the full extent and intensity of the glow we detect, especially in the most remote regions. This leads to more exotic explanations. The halo is a dynamic place shaped by constant accretion. When large clouds of gas fall in at high speed, they can collide with the existing halo material, creating immense shock waves. These shocks can heat the gas to millions of degrees, ionizing it directly and causing it to emit its own faint light. Each merger event, each stream of incoming material, could therefore be powering its own localized glow, a sign of the halo's ongoing violent construction. The most speculative idea points to the invisible majority. Could the ionizing radiation come from the dark matter itself? Some theoretical models propose that certain types of dark matter particles could decay or annihilate with one another, releasing a trickle of energy, including photons capable of ionizing hydrogen. If true, the diffuse glow of the halo's gas would be a direct, visible signature of the dark matter's hidden interactions, a faint shimmer from the universe's greatest mystery. Mapping this tenuous plasma is a monumental technical challenge. It requires instruments capable of detecting extremely specific, faint wavelengths of light emitted by ionized hydrogen, filtering out the overwhelming glare from stars and the background sky. Each new map reveals a more complex structure, with filaments and bubbles suggesting the ionizing energy is not uniform, but channeled and focused by magnetic fields and past events. Understanding this diffuse glow is critical because it represents a major, yet often overlooked, component of a galaxy's total mass and energy budget. It is the medium through which everything else moves, the hot wind that shapes the orbits of dwarf galaxies and the inflow of new gas. Solving the mystery of what lights it up is not just about finding a power source, it is about understanding the energetic balance of an entire galactic ecosystem, from the brilliant disk to the darkest, most ethereal reaches of its atmosphere. The heart of Andromeda itself holds a secret that echoes in its distant halo. At the very center of that majestic spiral, astronomers discovered not one, but two brilliant peaks of light, a double nucleus. One is brighter and slightly offset from the true gravitational center, a strange arrangement for a galactic core. This cosmic oddity is not just a curiosity of the inner galaxy. It may be the master key to understanding the chaotic population of the inner halo. The leading theory is one of a cataclysm. Billions of years ago, a substantial galaxy, perhaps one-third the size of Andromeda itself, did not merely graze the outskirts. It plunged directly into the heart of the giant. In the unimaginable violence of that merger, the smaller galaxy's core, a dense cluster of stars surrounding its own supermassive black hole, survived the initial impact. It began a long, decaying dance around Andromeda's original central black hole, slowly spiraling inward over eons due to gravitational friction. That infalling, dancing core is what we see today as the brighter, offset nucleus, a fossilized bullet lodged near the galactic heart. But the collision did not just affect the center. The force of such a head-on impact would have been staggering, sending shockwaves through the entire galaxy. The smaller galaxy's outer layers, its stars, globular clusters, and dark matter, would have been violently stripped away and flung in all directions. Much of this debris would not have escaped entirely. Instead, it would have been captured into highly eccentric orbits, forming a chaotic, hot population of stars in the inner regions of the halo. This material would not settle into the neat, flattened disk or the smooth, ancient outer halo. It would create a puffed-up, dynamically heated component, a splash of foreign stars with unique motions and chemistries. This is where the connection becomes tangible. The chemical fingerprints of stars in the inner halo could provide the evidence. If the double nucleus is indeed the remnant of a massive merger, then the stars scattered from that event should share a distinct chemical signature, different from both Andromeda's native stars and the metal-poor stars from smaller, devoured dwarfs. They would be the siblings of the stars in that offset nucleus, a family torn apart by the collision. Finding and mapping this specific population in the inner halo is like finding the scattered pieces of a shattered asteroid after an impact. Their orbits, when traced backward, might all converge not on a stream in the outer halo, but on a single, catastrophic point in the distant past, right at the galactic center. The double nucleus, therefore, is more than a central anomaly. It is the scar of the wound, while the inner halo holds the blood spatter. By studying the motions and compositions of stars thousands of light years from the core, astronomers are indirectly investigating that ancient defining trauma. The halo's chaos may not just be a record of many small meals, but the lingering echo of the one colossal feast that fundamentally reshaped Andromeda's very heart and set the stage for everything that followed. Andromeda's past is written in its halo, but its future is already circling in the dark. The third largest galaxy in our local group, the beautiful Triangulum galaxy, known as Messier 33, is not a distant neighbor. It is a satellite bound by gravity to Andromeda, and its orbit is a slow cosmic countdown. In billions of years, the graceful spiral of Triangulum will meet the same fate as all those ancient dwarfs. It will be consumed, its stars and dark matter shredded and woven into the ever-growing tapestry of Andromeda's halo. This is not a distant speculation, it is a destiny written in their mutual motion. Right now, as we observe them, the process may already have begun. The immense gravitational reach of Andromeda is likely stretching Triangulum, pulling tendrils of gas and the faintest outlying stars from its grasp. These could form a faint, tenuous bridge between the two galaxies, a ghostly highway of material that is the very first stitch in their eventual merger. This bridge would be a precursor, the initial thread of what will one day become a spectacular new stellar stream or shell within the halo, a future chapter of the archaeological record we see today. Observing this system is like watching the opening scene of a film whose ending we already know. By studying the current interactions, astronomers can test their models of galactic collisions with unprecedented detail. They can watch how tidal forces begin to warp a large, structured spiral before the final act, how gas is stripped and compressed, potentially triggering bursts of star formation in both galaxies even before they fully combine. Triangulum's own halo, a sparse collection of ancient stars and globular clusters, will be the first layer to be peeled away and assimilated. Its distinct chemical signature will one day mingle with the others, adding a new, rich metallic layer to Andromeda's outer reaches. This impending merger reframes everything we have explored. The 25 strange objects are not just relics of a finished story, they are clues to a cycle that is still turning. Andromeda is not a completed masterpiece, it is a work in progress, still gathering material, still writing its history with every gravitational interaction. The halo we see today is a snapshot of construction up to this moment, but it is a foundation for structures yet to come. The eventual fusion with Triangulum will be the next great accretion event, perhaps the last major one before its own colossal merger with our Milky Way. It reminds us that galaxies are not static islands, but dynamic, evolving beings born from chaos, built by destruction, and forever growing in the dark. From stellar ghosts to dark matter clues, the halo is a gallery of cosmic anomalies. Each strange object, from the faintest ultrafaint dwarf to the brilliant flare of a runaway star, is a single piece in a grand archaeological puzzle. Together, they reveal a history written not in peace, but in relentless violence and quiet cannibalism. They show us a galaxy that grew not from solitude, but from an endless series of collisions, captures, and mergers, each event leaving its own unique signature in the darkness. This is not a static museum, but a dynamic frontier where ancient relics coexist with newborn stars, where invisible matter sculpts rivers of light, and where the past continuously reshapes the future. By deciphering these 25 mysteries, we are not just studying Andromeda, we are holding up a mirror to our own galactic home. The Milky Way possesses its own vast and complex halo, its own streams of devoured galaxies, and its own population of enigmatic wanderers. In understanding Andromeda's violent, creative, and ongoing assembly, we glimpse our own history and our ultimate destiny when these two giants will themselves collide and merge. The universe's story is written in the halos of its galaxies, in the faint light of the consumed and the strange paths of the survivors. Which of these cosmic oddities captured your imagination the most? Was it the hypervelocity star flung from a black hole's grasp, or the tidal dwarf galaxy struggling to be born from destruction? Share your thoughts, and if you are ready for more journeys into the dark, subscribe for our next deep dive into the universe's greatest mystery.